Hello and welcome to another review session for your final exam in Calculus 3208 from CDLI as always. Today we're nearing the end. We've got a few more sessions here in Unit 7. We're talking about areas, definite integrals, and the fundamental theorem of calculus. Wow. Sounds fundamental. Here we go. So we're going to talk first of all about developing the fundamental theorem of calculus in terms of rate of change and total change. Boy, that's a huge idea. It's abstract for one thing, but it's so important. And the fundamental theorem of calculus and some notation related to definite intervals. And we're going to use the fundamental theorem of calculus to find areas under curves. So let's get rolling. Okay, small changes add up, you betcha. So let's take a look. We're going to start without looking at all the details. I just want to talk about a function first of all. Let's say I have a function f of x. Okay? Let's say it's continuous and it's also differentiable everywhere on an interval from a up to b. All right. So let's also say that since it's differentiable, that its derivative, f prime of x, represents its rate of change. Well, that stands to reason. Okay. So now I want you to jump way over to the right-hand side here, over here. This is a graph of, not f of x, but its derivative, f prime. Okay? So we have a graph of f prime of x here. And what I want you to consider for a second is, what would we do? Let's say this is the interval AB that we were talking about. So the graph up here doesn't represent f, but f prime, and it's still the same interval for x though, from a to b. Let's consider one rectangle that we could use in this interval if we wanted to, for some strange reason, I don't know, find the area under the curve of f prime. Okay? So think about that for a second. And I want you to think that the width of that one particular rectangle is our delta x, and if it's the first one, it would be x1 subtract x0 as always. Okay, now we're going to look at something else for a second, keeping all of those details in the back of our mind. Let's say I wanted to find the amount of a small change, delta f, in the original function f of x. Well, the amount that something changes, like let's say the amount your distance changes, is equal to the rate of change multiplied by how much the variable that you have a rate of change with respect to changes. What? Here's what I mean. The amount that your distance or displacement would change would be your speed multiplied by time, or how long you were moving. So in other words, if I wanted to find your change in displacement, it would be your, if we're talking about something linear or really small for an approximation now, it's your velocity times time. D equals vt is another way. This is another way to say that. But in this case, we're only talking about a little tiny change of any function, not necessarily a distance function. And we take its rate of change and multiply by the change in its independent variable, which is kind of like the time. Okay? So another way to say that would be that the little change in f would be the value of its derivative multiplied by delta x. Now, I'm going to think of the value of its derivative, which might change over the entire interval that we have for our delta x, but we're going to approximate it. Notice these little squigglies. We're approximating that just at the left endpoint of that interval, right here. Okay? So for the first sub-interval over here on the graph, if I took f prime, which is the height of my curve, or the height of this rectangle, and I multiplied it by that little bit of delta x, I can think of that as representing a little bit of a change in my original function, f. That is the key concept. Then on the next subinterval, I'd get another little bit of a change in f by taking f prime at the next endpoint, which would be x1, multiplied by delta x again on our second subinterval. And I can do that on all the subintervals. So what does that mean? Okay, so this is where we get to the crux of this thing. If I add up all the small changes in f, I would get the total change in my original function f of x over the interval that starts at a and ends up at b. So basically, it's the value of f at b subtract the value of f at a. And that's going to be the sum of all of the little rates of change, or the heights of all the rectangles, multiplied by the widths of all the rectangles, which is the changes in x. Okay? So notice that this function out here, f, and this function in here are related, f prime, this one is the derivative, this one is the original, or we could say that if f prime is the original, then this one would be the antiderivative. Now, we're getting somewhere with this. How do we take that total change and change it so it's not just an approximate thing anymore? Same way we did with Riemann sums. We take the limit as n approaches infinity of that expression, and that will be exactly equal to the total change in f. Okay. And what we're going to do is we're going to throw in some nice notation. Do you see how disgusting this is? We've got to write limit as n approaches infinity, I equals 0, sigma n minus 1, f prime of xi delta x. Gross. We simplify that a lot, and we write it this way. And you'll recognize the symbol from when we talked about indefinite integrals. But when we write an indefinite integral, except we put these little things on the end to indicate an interval a to b, then it becomes a definite integral. And a definite integral doesn't give us a function, it gives us a number that's equal to the total change on that same interval of its antiderivative. That, ladies and gentlemen, is the fundamental theorem of calculus. All right, let's have a look at this. Using the fundamental theorem. So remember, this definite integral is equal to the total change in the antiderivative. And it's also equal to the limit of the Riemann sum, so it's equal to this area. Okay, so if I wanted to find the area under the curve, all I'd have to do is find out, well, what's the antiderivative of this? And then evaluate it at b and at a and subtract them. And that's where we're going. So I want to take the integral, in this case, from 1 up to 2, and that's how we say it, of f of x, which is 4 minus x squared, dx, always have the dx, and why do we have that dx? I forgot to mention that. So bear with me for 1 sec while I jump back. Notice here when I took this limit, delta x was the change, right? And remember we said as the number of rectangles gets really, really huge, what's going to happen to the width of each rectangle? It shrinks, and it gets infinitesimally small. So that delta x there, when we take its limit, turns into dx, which is just this notation that we use to represent a super tiny infinitesimal delta x. That's all that is. So I can't have an integral without a dx. It's got to be there. That's where it comes from. So I want to evaluate this. And what we're saying is I find its antiderivative, and then I evaluate at both endpoints and subtract them. So the antiderivative of 4 minus x squared, that's going to be 4x minus x cubed over 3. And I've got to evaluate at 4 and 1 and subtract them. See this funny notation, this giant bar that I wrote? That's just one way to write out the fact that I want to evaluate this in this way. There's another way that's probably as common. You could write, instead of that, if you really wanted to, you write 4x, and some folks prefer this, minus x cubed over 3, and then you could put it in square brackets like that, and then put your limits outside from 1 up to 4. Either way, up to you, both acceptable. All right, so now what this means is I evaluate at 4, and then I subtract what I get when I evaluate at 1. So let's try that. So at 4, I'm going to have 4 times 4 minus 4 cubed on 3, and I have to subtract what I get when I have 4 times 1 minus 1 cubed over 3. Okay, so I have to put all that together now. So to put all of that together, I'm going to need some space. Oh, I'm going to write it back this way. I'm really sorry for being sloppy with that. So I'm going to write it back this way. So this is going to be 16 minus 64 over 3. So I've got 16 minus 64 over 3. So I'm trying to save a little bit of space here, so I apologize. But 16 over 3 is, of course, 48 over 3. So this is 48 minus 64 over 3 for what's in the first set of brackets. And then I have to subtract 4 minus 1/3, which is 12 minus 1 over 3. Okay? So this first one here is going to give us a value of, let me see, 48 minus 64 is negative 16. So I've got negative 16 there over 3, and I have to subtract 11 over 3. Okay, so hang on 1 sec here, something's fishy. What do we got mixed up here? Oh boy, look, this was supposed to be a 2, and in my great absent-minded fashion, I made it a 4. Yipes, we gotta fix that. That's gotta be a 2. That's gotta be a 2. That's gotta be a 2. Over here, those guys are gonna be off, but that's only a quick fix. Just give me 1 sec now. We can tidy this up. Sorry about that. So let's get rid of this stuff. Alright, so this is going to be 4 times 2, which is 8 minus 8/3. Okay, so that's going to be 24 over 3 minus 8 over 3. So 24 minus 8 over 3, and then I have to subtract 4 minus 1/3. So that's going to be 11 over 3. So I have 24 minus 8 over 3, which is 16 over 3 minus 11 over 3, or 5/3. Sorry, 5/3. So the area of this curve, under this curve in here, is exactly 5/3. And we find that by evaluating that definite integral by the stuff. Evaluating definite integrals gives you the area under the curve. Cool. Let's find another one. Determine the exact area under the curve of f of x equals x squared on the interval from 0 to 1 using the fundamental theorem. Well, it's pretty straightforward. The area, and I know it seems really complicated when you look at the big explanations, but let's see how easy it is. We got to go from 0 up to 1 of x squared dx. That's all there is to it. So what that means is I use the antiderivative, which is x cubed over 3. Notice that I don't need to add a constant plus c to this, and we can talk about why, but that will come at a later time. So for a definite integral, I don't need that, and I just go from 0 up to 1. So I evaluate it at 1. So it's going to be x cubed will be 1 cubed over 3. And then I subtract what I get when I evaluate at 0, so that's 0 cubed over 3. So that's 1/3 minus 0 is just 1/3. And if you watched our last video, we found that in a much more complicated way, using lots of limits and sum formulas and sums and all kinds of crazy things, but it's just 1/3. All right, let's try this one. Compute each of the following definite integrals. So you can think of these as being areas. So if I were to graph this linear function and look between x equals 3 and 7, what I'm finding here for my answer would actually be the area of that. But let's see what we get for this first one. Well, we take an antiderivative, so it's going to be 17x squared over 2 plus 4x, and I have to evaluate at 3 and 7 and then subtract the top one from the bottom one. So this is going to be 17 times 7 squared all over 2 plus 4 times 7. And then I have to subtract what we get when we take 17 times 3 squared all over 2 and subtract 4 times 3, like so. All right, so let's see what a magic calculator is going to give us for that one. So save ourselves the agony of working it all out and save you the time of watching me work it all out in a cumbersome way. So let's go to magic calculator. Okay, my magic calculator tells me that this should be 356. Okay, so just doing arithmetic from there gives us 356. Let's do the second one now. So this one, I'm going to use this space and then we'll erase it after. So I've got to go from -1 up to 1. Those look like friendlier numbers. So I'm going to just take an antiderivative for that. So 5x to the power 4 will be just x to the power 5. 3x squared gives me x cubed. And then 9x. And let's use that other notation, just so everybody remembers that there's 2 of them. And we can go from -1 up to 1. So that's going to give us 1 to the power 5 minus 1 to the power 3 plus 9 by 1. And I have to subtract what I get when I take -1 to the power 5 minus -1 cubed plus 9 by -1, like so. And I put all that together, so these disappear, and I just get 9 from the first one. And over here, I've got -1 subtract -1, so they disappear, and I get -9 from there, but I'm subtracting it, so I get a total value of 18. Okay, so let's go back now and do the third one, the very last example that we have there. Let's erase all this junk out of the way. Use the left-hand side to do the question from the right. Let's just move this stuff over, and then over there. There we go, that's better. So let's evaluate this last one now. So the integral from 0 to 9 of that stuff. Well, I cannot take an integral, definite or indefinite, at this stage of the game unless it's written like a polynomial. So I'm going to take x squared minus 3x over square root x. and I'm going to try to change that into a polynomial by simply taking this square root, getting rid of it, and changing it into an exponent of 1/2 on x, like so. So then I subtract my exponents to simplify this into a polynomial-like form. So I have x to the power of 1/2, or 3/2, minus 3x to the power of 1/2 times dx. And I should keep those brackets hanging about. And when I do that, I have to increase the exponent by 1. So it becomes x to the power of 5/2 divided by 5/2, or times 2/5. And then I have to subtract 3 times x to the power of 3/2 multiplied by 2/3, so the 3's will cancel and just give me a 2 there. And then all of that, and you can just use one bracket if you like, or a straight line. And I'm going to evaluate from 0 up to 9. Okay, so evaluating at 9, I'm going to get 2/5 of the square root of 9 all to the power of 5 minus 2 times the square root of 9 cubed, and then I have to subtract both of these. Evaluated at 0 will be 0. Okay, so the square root of 9 is a relatively friendly number. It's just 3. So when I evaluate those things, I'm going to have 2/5 of 3 to the power of 5, like so. And I have to subtract 2 times 3 cubed. So let's see, 2/5 of 3 to the power of 5 minus 2 times 3 cubed, which is 27, gives us 43.2. So 43.2 is the exact area under that curve on the interval, that curve on the interval from 0 to 9. Okay, your turn question. Just a couple of definite integrals for you to evaluate. So good luck with those. Have lots of fun. Here's your solution. So hopefully you're getting the right things. Those are a little less complicated in terms of the arithmetic than the ones that I made myself do, unfortunately. And here are the key ideas. So if we want to find the exact area under a curve, we remember that we can find it by taking those limits. And so for some special functions, we saw ways to do that with some formulae. But now what we have is this integral notation that does it really handily. So the integral from a up to b, and we have the fundamental theorem of f of x dx is just equal to big F of b minus big F of a. And that's our much more convenient method that we've now developed. Thank you very much. Good luck studying. Hopefully that was helpful.